Welcome to the Equilibrium Lab. Today we will be making iron thiocyanate complex and testing the equilibrium constant for the formation of this out of iron, aqueous iron, and aqueous thiocyanate, which is SCN minus. To do this, we need actually four different solutions. We'll need iron, which is 2.5 times 10 to the negative third iron nitrate in a 0.5 molar nitric acid solution. Nitric acid is just to ensure that the iron remains 3 plus. We will need 0.5 molar nitric acid. That's going to be our solution that we're going to dilute everything with. So when it comes to making any dilutions, we're going to be using that instead of water because we want to keep the general concentration of that about the same. We're going to use a concentrated 1 molar KSCN, potassium thiocyanate, 1 molar. We're going to use that to make concentrated. And we're going to use a 2.5 times 10 to the third molar KSCN. We'll use that for the second part. This lab is going to be split into 3 different steps. Step 1 is making dilute iron thiocyanate. Step 2 is going to be getting a calibration curve where we measure the iron thiocyanate at different concentrations to try to get a linearity curve for the Beer's law plot. Step 3, using that curve, we are going to finally test for the equilibrium constant K. We're going to need ice tables and all that. So what are we going to need? We're going to need a bunch of beakers to get our solutions. We're going to need a volumetric flask and a volumetric pipette. Volumetric only has the 1 mark on it because it's only scheduled to measure 1 volume. And at least a couple graduated pipettes. Notice that you have multiple markings. They'll be ideal for making multiple solutions. And finally, some test tubes. We need some test tubes to make our solutions. Oh, and we'll need a glass stir wad. And finally, we'll need our lab quest with SpectroViz setup. So we'll deal with that when the time comes. See you in a few minutes as we do steps 1 through 3. Part 1 is to get our solutions and to make our dilute iron solution. So we need approximate amounts because this is going to be used. We have approximately 50 mils of iron. We're going to get approximately 35 mils of the concentrated thiocyanate. And approximately 150 mils of our nitric acid. 140 mils. We're going to use that for all our dilutions. I have a waste beaker here. So I'm going to coat the sides of this with my iron solution, just a little bit, just to make sure that this is all iron and not like extra anything out. I'm just trying to coat the sides so that we get the best concentration possible. Scrape that out. Okay. Put that in the waste beaker. Now I'm going to put in exactly 10 mils. So I'm not going to zoom in on this or anything like that. You don't need, as long as I get this on the spot, we can feel confident that it's exactly 10 mils. I press the release gauge and it's all being transferred into here. Do, do, do. Okay. I'm done with this piece of equipment. Now I have to dilute this with our nitric. Here's where it might be a little tricky. No, I don't want to spill on the book. I'm not diluting with water, we're diluting with nitric acid. Not super concentrated, but if you were to get this on your skin, you would wash it off. So after a little bit of quiet, I'm trying to concentrate. I've slowed down, it is not quite there. We're almost there. Carefully. Oh, that's pretty darn good. I'm going to stretch my parafilm over this. Stretch this over. Oh, almost lost the parafilm, which would have been great. See right there. Now I'm going to invert it 4 or 5 times. And this is going to make my dilute ion. And I'm going to use that for the next step. This part is we're making our solution of iron thiocyanate for our calibration curve. We're going to make 5 test tubes, each with differing varieties of dilute iron, such that KSCN is in such high concentration that iron is definitely the limiting reagent, and thus we're going to assume this goes to completion much like a strong acid would. The amount of iron thiocyanate is going to directly correlate to the amount of iron we've added. So first thing is to coat the sides of our graduated pipette, best of our ability, and dump that coating into the waste. Notice the waste is turned red. That is because iron and thiocyanate form this red complex. Suck up best of my abilities 5 mils and dispense 5 mils into each of these tubes. We're not going to zoom in on this because, well, we're going to assume if I'm doing this right, we're going to get it good. 1, 2. our first 5. Our second 5. Our third 5. Our fourth 5. Our last 5. With that, we put this away for now. We are done with the concentrated KSCM.
Boys, my arm's sore.
Now, to each of these test tubes, I'm going to add differing amounts of iron. First, I'm going to once again coat this with my iron solution so that we do not have any dilution problems. But to test tube 1, we're going to add 1 mil. Test tube 2, we're going to add 2 mils, and so on and so forth. So once again, we're going to assume I'm going to do this right and not screw this up. That's the assumption you guys are going to have to make. Okay, to test tube 1, already a slight mistake. I've added not 1 mil, but 1.5 mil. So note that 1.5 mil added to the first one. To the second test tube, I have added 2.4 mils. I'm going to do my best to add the correct amount to the third one. Once again, we're going from what we get. That one I added 3.1 mils. Up. To that test tube, I added 4.1 mils. And to the last test tube, I added 5 mils. Should be able to see I'm not quite done with these yet, but you can already see there's a slight difference in the color. but I will present the final data. This last one is I'm adding nitric acid to dilute our things, so they're approximately the same volume. Once again, I am coating the sides of my graduated pipette so that whatever was in there doesn't affect it. Okay. Now I'm going to add differing amounts to each one so that the final volume should be about the same. Let's see if I can get, I'm going to shoot for what I got, and I'm going to give you the actual results based on what I actually get. .5. .6. Let's say 1 or 2.0. Finally, I should be shooting for 1, and I don't add any to the last one. So now you see the volumes of these are about the same. You can kind of see them just barely cresting over the top of the little holder. The last part of this step is to just stir these guys to make sure they're well mixed. And of course, clean the stir rod between each, clean and dry the stir rod between each sample. We are now ready for step 3. Okay, I have this all warmed up. I need to
I need to calibrate this, measure the lambda max and the absorbance of all 5 samples at the various wavelengths. There is one error in the write-up. They ask you to calibrate this with deionized water, and that makes very little sense. We have not diluted this with deionized water. We have diluted this with nitric acid. So we are going to have our standard calibration with nitric acid. Full chem wipe, wipe down the sides. Insert this, facing that way. I'm going to try to calibrate this. So it is already well warmed up, so I can probably skip that part. There's calibration. And I can hit OK. So it's basically zeroed out every part that is nitric acid. Pour that into my waste beaker over here. Now I'm going to measure the lambda max of sample 1. But one thing I want to do is first pour a little bit of sample 1 into there. Oh, a little bit too much. That's fine. A little bit of sample 1 into there to coat the sides. Put this in here. Measure my lambda max. So hit play. Stop. If you remember wavelength of light, where that red, the sun that appears red, should absorb in the orange, yellow, green, bluish region. And our lambda max, as we see right here, is 485.8. And we're going to set it so that all of our samples will be run at 485.8. And at that wavelength, absorbance of 0.311. I have changed it to events with entry from the little mode button, and so that it'll only record at 485.8, and I'm going to recalibrate it like it asked me to. See if we get any different numbers. So. Probably not, but just to make sure. In there. Sensor. Calibrate. And then from there, we will run all 5 samples. I'm going to work from low concentration to high concentration so that when I dilute it, it's going to be less of an effect. Okay. Pour that into my waste. Coat the side with a little bit of my sample 1 again. Right down the side. Make sure there's no air bubbles. Clear. Transparent. Go ahead and play. Record, 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 and stop. Okay. So we got our first value, 0.294. It's changed just a little bit. Dump that out. And start with sample number 2. Oh, a little bit too much. That's okay. Sample 2 is ready. 0.587. Dump that in there. Sample 3 ready. .723. Sample 4 ready. Pouring it in. Cut it on the sides. Dump it out. You know, it seems very wasteful, but I have excess for this reason. Read that, and that's 0.967. 0.969. And the last sample, sample 5. Same thing, coat on the sides. Air bubbles, no smudges. No air bubbles, no smudges. Put this in. Last one. .110. Now I'm going to save these for now on the off chance we need them, but we should be done with them. At this point, you have everything you need to make this standard curve. You need to calculate what is the concentration of iron. You will use your M1 V1 equals M2 V2 to calculate first what is the concentration of dilute iron from step 1, and then what is the concentration of iron in each test tube by using the volume of iron versus the total volume and the concentration of your dilute iron. From there, you can plot the concentration of iron versus the absorbance and put a trend line through that. That trend line will be used to calculate the concentration of iron thiocyanate in your unknown solutions and step and part B. In this step, we'll be making our solutions again. The main difference now is that the iron and the thiocyanate are going to have equal initial concentrations. As we mix them together, neither one is in large excess. So we have a very valid equilibrium expression. We don't know how much iron is consumed or how much thiocyanate is consumed, and we'll need an ICE table to determine that. So for each of these 5 test tubes, we will be putting 2.5 times 10 to the negative third molar iron into them, and then adding different amounts of thiocyanate and nitric acid to them. I've already washed this with the iron solution. I am going to add 5 mils of iron to each one, hopefully to some extent. The first one, this one's a lot better. 5 mils added to the second one.
5 mils added to the third one. Five mils to the fourth one. Five mils to the fifth one. Now 5 mils of iron added to each and every test tube. Once again, I've already rinsed this pipe head with KSCN, correct concentration, and I'm going to try to get 1 mil into the first one, 2 mils into the second one, and so on and so forth. I will report exactly how much. So, shoot, that was, well, let's say about 1.3 mils to the first one. 1.3. 2 mils to the second one. 3.1 mils to the third one. 4.2 mils to the fourth one. And 5 mils to the fifth. I've already washed this one, but I'm adding nitric acid to make the concentrations the same. 4.15 mils, 2.9 mils, 2 mils exactly, 1 mil exactly, and I add 0 to the last one. I also just stir these, and now you'll notice that these have a little bit different heights, but that is due to the diameter of the tubes. We're ready for the final step prior to calculations.
I now begin the process of measuring the absorbance of all 5 test tubes. Once again, rinsing out. Pouring it into the waste. And this waste is a little bit less red. Enough. So, first one is 0.020. Second one, 0.034. Moving on to the third. Point 0.037. 0.056. Finally, 0.066.
At this point, we can dispose of all of our chemicals. We are ready to begin our calculations. We, we are going to calculate the concentration of iron and thiocyanate at the initial steps before we mix them. So we're going to take our 2.5 times 10 to the negative third molar and the volume we used and calculate its dilution. You're going to do the same thing for both iron and thiocyanate. The equilibrium concentrations of iron and thiocyanate are unknown, as is the change, but the change is equal to the concentration of iron thiocyanate. And we can calculate that based on the absorbance. And that's why we did that calibration curve in part 1. So if we find the equilibrium concentration of iron thiocyanate, we know the change. If we know the change, we can calculate the equilibrium concentration of both iron and thiocyanate. From there, we use all three equilibrium concentrations to calculate K. Now, let me warn you, if you try to do this with your calculator, it may take a while. If you can set this up in an Excel spreadsheet, you can beat through this with relative ease. You set it up for trial 1, test tube 1, and if you do it correctly, you can drag down the equations and solve all of them at once and be done. This is all you need to do to solve this, and then the rest of it is like answering some post-lab questions. Always, if you I may have made a few mistakes in there, you may have noticed something here or there. There may be some error in the data. If you can point out any mistakes I've made, maybe they're worth extra points, but maybe I'm perfect. Maybe there was no mistakes. It's up to a careful, close observer to find out.